Hello everyone, welcome to the recorded session on chlorination. And welcome back from your break. I hope it was a restful break, maybe some catch-up. You could get some catch-up done on the course. Anyway, so we are in part 2 of the semester, and we are going to start with chlorination. Let me go over the objectives, and then we'll just jump right in. Here we go. So, by the conclusion of this week, not just of this lecture, you will be able to list 3 of the major factors contributing to chlorine disinfection effectiveness, explain breakpoint chlorination. Once again, we're going to revisit that. Identify the variables in a chlorination CT ratio and calculate the CT ratio. Describe some of the personnel safety hazards inherent in the use of gas and liquid chlorine. Name 2 of the common gas chlorine container sizes. Explain how chlorinators and hypochlorinators are operated. The overview of points of application in a treatment plant. You will be able to calculate the chlorine demand given a chlorine dose and residual. And given a plant flow rate and a desired chlorine dose, calculate the chlorine required in 24 hours. And then also you will name an improved method of measuring chlorine residual. Now, in the disinfection lecture, we covered chlorination a little bit. So some of this is going to be repeated, and that's okay. Repetition is good. So let's start with the forms of chlorine used. We have gas, solid, liquid, or on-site generated. Gas is available, the chlorine is available 100%. In solid form, or calcium hypochlorite, it's available 60 to 70%, and in liquid form, sodium hypochlorite or bleach, it's available in 5 to 15% chlorine availability. And then if you do generate the chlorine on site, it would be 0.5% to 8% available chlorine. So the types of chlorination methods, again, is effectively listing what we just talked about. So you have gas, you have the hypochlorites, sodium, liquid or solid. You have chlorine dioxide and chloramination, which we haven't talked about too much yet, just a little bit. When we looked at the breakpoint chlorination curve. So factors influencing chlorination, the pH. The chlorine disinfects better at lower pH. Chlorine is better at higher temperatures. The turbidity will affect the disinfection of chlorine, and by chlorination, it will decrease it. And the presence of reducing agents like hydrogen sulfide, ferrous ions, manganese nitrates, and ammonia will also decrease the effectiveness of chlorination. So, points of chlorine application. There are, during the whole treatment process, there is a time, often when chlorine is applied at pre-chlorination. When I say pre-chlorination, I mean that it's done pretty much right after the first 2 steps in the treatment process. So, when you use chlorination at this time, it's a touchy time for creating trihalomethanes, because the water at this point is going to contain a lot of, it's possible that it contains organic material. So that's the risk that you take with that. But some of the things that it can do is control algae and slime, control mud ball formation. It helps improve coagulation. It can reduce tastes and odors. And it can increase the chlorine contact time, and it increases your safety factor for heavily contaminated waters. And then post-chlorination is another point where it's where you chlorinate right as it's re-entering as it's entering the distribution center. So it's another chlorine application at that point. Then also in wells, in distribution systems and mains during post-construction. When a new water main is constructed, it goes through heavy chlorination before it is put into service. And then also it can be applied at the actual steel tank or reservoirs in the system. So, chlorine residual and dosage. Here are the typical residual amounts that are desired in the clear well. It should be 0.5 milligrams per liter. The residual at the end of the system should be 0.2 milligrams per liter. And the formula for chlorine dose equals the demand plus the residual. And I think you've already covered that before. Contact time is required, and that CT value, which is not the contact time, it's the CT value. Contact time, as you see here, is a factor in that. So it would be the residual, whatever your residual is at the time, times the contact time. That is your CT value. Be careful. That is something that often students get tripped up with that on tests. So contact time is different than the CT value itself. Okay. So, again, this is a little bit of review about how chlorine reacts with water. So when chlorine is added to water, it reacts with the organic compounds to form trihalomethanes. Then it can also react with ammonia to form chloramines, and that, if you are using chlorination, that would be the point in your process where you would stop adding chlorine. It also reacts with hydrogen sulfide, which can cause odors, and it reacts with the ferrous, manganese, and nitrite ions. And what is known as demand is the fact that the chlorine that is added is losing its disinfecting properties. And as we looked at the breakpoint curve, you will see a little bit more of what that means. We're going to review that in just a second. So, using chlorine gas. So the chlorine gas plus water forms hypochlorous acid and hydrochloric acid. The hypochlorous acid is the most effective form of free chlorine residual. It breaks down further into hydrochloride ions, which is a less efficient disinfectant than the hypochlorous acid. This reaction also depends on the pH of the water itself. The lower the pH, the more efficient, and the higher amounts of hypochlorous acid are created, which is your free chlorine residual. And the higher the pH, the less the disinfection efficiency, and higher amounts of hypochlorite ions are produced. So here is our famous breakpoint curve, breakpoint chlorination visualization, if you will. So here, what we just call the chlorine demand, this is where that initial dose of chlorine is used up really quickly, because that's your initial dose. That's when everything is going to take away the disinfection property of the chlorine. It's going to use up the chlorine. Then as you keep adding chlorine, this is your combined residual, where the chloramines are formed. And then this is the next step is where the chloramines start to be destroyed, and that goes until such a point where it reaches the break point. And after that break point is where everything else is free chlorine residual. In other words, the amount of chlorine that you add to the system it can disinfect to that proportion in the system itself. Okay, so using hypochlorites, this would be basically the solid or liquid form. They are less pure than chlorine gas and less dangerous. They decompose in strength while in storage. The temperature, light, and physical energy can break them down before they react with pathogens. And however, they do react, the chemical reactions are similar to chlorine gas, where you would get the hypochlorous acid plus calcium hydroxide with calcium hypochlorite, and with sodium hypochlorite you would get the hypochlorous acid plus sodium hydroxide. The main difference between gas and hypochlorite is how it's fed and how it's stored, how it's fed to the water, how it's distributed. Using chlorination. Chloramines are produced by adding Cl2 glass or hypochlorite to produce the hypochlorous acid, as we've already mentioned. Then more ammonia is added to the hypochlorous acid to produce monochlorine, and then more hypochlorous acid is created to create di- and chloramines. There are 3 types of chloramines formed depending on the pH. The monochloramines are what you're looking for. That's the combined chlorine residual. That's what you're going to use to chlorinate with. The dichloramines are weaker than the Cl2, but they are more stable, so they can be used in a distribution system. And then the trichloramines may form tastes and odors. So they are the least desirable of the 3. Chloramines can be broken down by bacteria, heat, and light. They are less effective as a disinfectant than free chlorine. They kill bacteria and some parasites, but they are ineffective at killing viruses. Odors can be caused also by chloramines. Instead of cutting back the chlorine, keep adding free chlorine until free chlorine residuals are present. And that's a little bit counterintuitive, because once you get that chlorine odor, you think, well, I should stop adding chlorine, but you really should add chlorine until there are free chlorine residuals present once again. And then also what can happen is incomplete nitrification. The free ammonia helps form ammonia oxidizing bacteria that can actually deplete the residual. So that's not a good thing. I think I'm going to stop there. This is part 1. Stay tuned for part 2. We're going to start with chlorine dioxide. Thanks.